Okay, guys, here is the problem that we started in class. We talked about what we didn't finish. So I'm going to try to go through these really quickly because I only got about 10 minutes on the file for the video. So hopefully it helps you guys. A window consisting of a rectangle topped by a semicircle is to have an outer perimeter P. Now this problem doesn't give us the value of P, so I'm going to assume that this is a constant. Um, but we're going to need the formula for the perimeter in just a second. Find the radius of the semicircle if the area of the window is to be a maximum. So we want to find the maximum area, so that's the formula that we're going to determine given some of the other information. So just labeling the picture here, I'm going to say this is R. If this is R, then this length here is going to be 2R. And I'm going to go and label this X. So the perimeter is going to be this here, which is half of a circle. So since 2 pi r is the circumference, half of it's going to be pi r. And I'm going to add that to 2x's and the 2r. Since I'm going to consider p to be a constant, I'm going to go and just solve for x since we want things in terms of r. So if I solve that, I'm going to have x is equal to p minus pi r minus 2r divided by 2. Now I'm going to take and find the area formula. The area is the area of the semicircle plus the area of this rectangle. So the area is the area of the semicircle, which is 1/2 pi r squared, and x times 2 pi r. I'm sorry, 2r. Since x times 2r, we know x is going to be this, so I'm just going to go and replace that right away. So p minus pi r minus 2r over 2 times r, 2r. I'm going to simplify this a little bit. Go ahead and get rid of that. And I'm going to multiply the r in. Now I could add these because they're like terms, but I'm going to go ahead and keep them out because it's just easier to do the derivatives later. So then once we have this a, we're going to go and take the derivative with respect to r. So we just use the power rule here and get pi r plus p, the derivative of r is just 1, 2 pi r minus 4r. Since this is what we want to have maximized, we're going to take that derivative and we're going to set that equal to 0. And we are going to move the p over and factor out an r. So when I do that, it's going to look like this. R pi minus 2 pi minus 4 equals negative p. Divide everything over. I can add these two like terms, which I'm going to do here. R equals negative p over negative pi minus 4. And just for simplicity's sake, I'll take out the negative. And I'll have that. So this will be the radius of the semicircle when the area of the window is at a maximum. Okay. So looking at our next problem here, we're looking at this rectangular field. And this field is going to be enclosed by a fence, and this fencing is only going to go up to here. This part is the building, so we don't need fence on the part of that part of the building. And this is the river, so we don't need any fencing there. So we're going to need X amount of fencing here. We're going to need X minus 20 amount of fencing here. And we're going to need Y amount of fencing there. Altogether, the area of this field is still just going to be X times Y. But the amount of fencing that we have is going to be X amount plus Y amount plus X minus 20 amount. So the amount of fencing, which we know is 1,000, because it tells us right here, 1,000 feet of fencing. is going to be x plus x minus 20 plus y. And so we're going to simplify this a little bit here. Remember that we want we want one variable. So we're going to have y equals 1020 minus 2x. We're going to go ahead and substitute that right here. X times 1020. And we want to find the dimensions of the maximum area. So area is, again, what we're taking the derivative of. So we're going to take the derivative, and as Min said, we're going to take the derivative with respect to x. I'm going to go and multiply this out here, just so we can use a power rule. 1020 minus 4x. We're going to set that equal to 0. We're going to solve for x here. And x is going to be, I believe, 205. And that's 205 feet. So if x is 205 feet, then we can just take this and plug it back in here and find out that y is 510 feet. That'll be the dimensions of x and y for the maximum area. Okay, so here's the last one that is on this worksheet. The interesting thing is that when I did this right after you guys left class today, I got an interesting answer. A lot of the numbers work out, but the answer kind of is strange. So we're going to go ahead and assume that the answer is correct, and I believe it is. But let's go ahead and go through this real quick here. A company manufactures cylindrical barrels. I'm thinking holiday here. So here's a barrel like this. We know that the top is going to cost us $10 per square foot, which is area. So we want to the area of the top. The area of the top is pi r squared. The area of the bottom is pi r squared. We add those two areas up and we multiply that by $10. That's going to be how much it costs for the top and the bottom. Now the outside, we can take the outside and we can spread it out, like pull it apart. If we pulled it apart, we'd have this rectangle that looks kind of like this. And the top of the rectangle, we can turn it around like this. It creates a circle, which is 2 pi r. It's the circumference. And then we have the height. So if we take this area, 2 pi r h, and we multiply it by $8, which is how much it costs per square foot, we're going to have the cost of the outside. We're going to add those up together, and this is going to be the cost of the can. We don't want to have things in two variables, so we're going to use the information here that each barrel holds 5 cubic feet. Cubic feet is a measure of volume, so we're going to use the volume formula, and we know that over here on the side here, I'm going to say that the volume is 2 pi r squared times h, and I know that's equal to 5. So I think the easiest thing to do maybe is to substitute for h, since we don't really want to have a square root to start with. So h is going to be 5 over 2 pi r squared, and we're going to go ahead and substitute that right here for h. Okay, so we're going to have 20 pi r squared plus 8 2 pi r. I'm going to substitute this in, so 5 over 2 pi r squared. The r goes through that one, the 2 pi goes there, and we're going to have 20 pi r squared plus, we got 8 times 5, which is 40, over r. And going to set that equal to c, and we're going to take a derivative because this is what we're trying to maximize. It says here we're minimizing the total cost. So this is the cost function that we're going to minimize. So we're going to take the derivative with respect to r in this case. So we're going to get 40 pi r. Now remember that the derivative, when the r is on the bottom, it's going to be r to the negative 1. So we're going to do minus 40 over r squared. This is a common derivative. You guys should kind of know that by now. Just using the power rule. Set that equal to 0. And I'm going to multiply everything by r squared to get rid of this on the denominator. So I'm going to have 40 pi r cubed minus 40 equals 0. R cubed equals 40 over 40 pi. And I'm going to get 1 over pi. So r is the cube root of 1 over pi. So this is going to be the radius. And to find the height, we can plug this back in here. And we're going to get h equals 5 over 2 pi r squared. So we're going to have the cube root 1 over pi squared. And maybe use a calculator on this. If not, you can put this as 5 over 2 pi times pi to, let's see, that's 2/3. So negative 2/3 since we have a fraction. And we could do a little bit more with that, I guess, and put the pi's together and simplify a little bit. But I think this kind of hopefully gives you the idea of what we're doing. And the most important thing, guys, here is that you've taken and found the cost function similar to that of related rates, where you had to find a function and then use some more information to plug it in to have one variable. You're doing the same thing in optimization. The only difference is here now we're not doing a rate in terms of time. We're taking the derivative and setting equal to 0. And I think you're pretty good with this. The setup is always the most difficult part. So hopefully you guys understand these 3 problems. You had an opportunity to work on them first and then look at the solutions, okay? So that's it, and I'll see you in class tomorrow.